Today we're going to be covering STAR-CCM, and I'll be giving an introduction to the software, going through a couple demos, and I've got a PowerPoint here that I'm going to go through, and if y'all are interested, you can download that PowerPoint as a handout through the GoToWebinar interface. So yeah, that's available. You can just straight up download it. Okay, yeah, let's just get started. My name is Glenn Andrew. A little bit about myself. I'm a stress analyst here at SDA. And yeah, so my background is in finite element modeling, and we're also selling STAR-CCM, so we're starting to get into supporting that software as well. So a little bit about today's overview. I'm going to talk a little bit about Structures.aero and then jump right into the STAR-CCM software itself. And we'll go over what the software is, like what it does, what it's capable of, how it solves and provides, provides you with data. And then we'll go through the user interface, and I'll actually open up the software and go through the user interface. And then we'll talk about the workflow and how you actually work in STAR-CCM, because it's definitely different from a finite element software. And then we'll briefly touch on geometry preparation and actually use the software. I'll give a couple demos, but I will be giving another webinar, and we'll definitely get into the details of how the software works and how to use it efficiently and effectively. So yeah, let's just move right along. So SDA, or Structures.aero, is a professional services company. We've been supporting mainly stress analysis since 1997, and we've got a team of about 15 engineers here, and we help our clients design lightweight and load efficient structures. So our staff is primarily bachelor's engineers with bachelor's degrees, but we also have a couple master's degrees and one PhD engineer. And we're actually growing, and our team has started to encompass not only stress analysts, but also design engineers. Some of the industries we service are, aerospace and defense is what you would expect, but we also work with marine, energy, and medical industries. And another note about our company is that we really specialize in composites. That's the bulk of the work we do here. And Femap is really the software that enables us to do that. So in terms of some of our customers, we work with a wide variety of industries, from the federal and space side to aerospace and defense, and then also electronics, medical, and marine. We're currently working on a couple projects with Blue Origin and Sierra Nevada, and then also NASA, Aurora Flight Sciences, but we've worked with all these companies in the past. So we've got really just like a broad connection with the industry, and that really helps us because we see a lot of things over the course of all these contracts. So we really gain a lot of experience that we're able to leverage with other customers. So in addition to providing engineering services, we are also a Siemens Value-Added Reseller, and we sell a lot of software, primarily Femap and NX, Nastran, but also plenty of other things such as NX CAD, what we're talking about today, STAR-CCM, also Simcenter 3D, and we offer training in Femap because that's the software we really use every single day. And we have an advanced class as well as an introduction class. We offer training in Fibersim, and then we also customize training if a specific customer says, hey, we want to learn more about this. So if anyone out there is interested, feel free to reach out to us, and if there's enough interest, we can for sure set up training classes. Right now it's a little bit iffy with the coronavirus. It's a little bit iffy to do in-person classes, but we're moving towards online classes so that we can really still continue to support our customers despite the pandemic. So, all right, so moving into STAR-CCM. Essentially, STAR-CCM it's a physics modeling software. and they've built out an incredible amount of functionality for simulating not only fluid flows, but electromagnetics, heat transfer, multi-phase flow. STAR-CCM, it runs like a core set of fundamental principles for each one of these physics scenarios, and that determines, a lot of different things that you have options for. So, with CFD, which is I think what STAR-CCM is really known for, it's used for modeling fluid mechanics basically across a wide range of flow regimes and fluid types. So you can model inviscid and laminar and turbulent flow. There's models for compressible and incompressible, porous resistance. If you've got like fluid flowing through like a catalyst or something like that, you can model gravitational acceleration, steady or unsteady simulations, different equations of state. For example, like if you've got constant density or you need to treat your fluid as an ideal gas. And then there's also turbulence models for different flow behaviors, especially if you are working in, a boundary layer type application. So in terms of electromagnetics, there's physics models that model the electric potential and magnetic potentials, so you can solve for resulting electric and magnetic fields. And these are used for modeling, magnetic fields induced by electric currents or permanent magnets, excitation coils, that type of thing. In terms of heat transfer, STAR-CCM comes with a database of common materials so that you can model different types of heat transfer, such as convection, conduction, and radiation. I think heat transfer and CFD are really probably the two physics phenomenon that STAR-CCM is really known for. And then everything else has been built up around it so that it's truly like a multi-physics simulation platform, not really just fluid dynamics. And then, so then you also have multi-phase flow, which is, accounts for distinct fluid phases within a simulation. So that would be of interest if you were modeling like transport or solid particles, liquid droplets, or gas bubbles in a continuous gaseous or liquid phase. So there's also models for particle dynamics, reacting flow, electrochemistry, aeroacoustics, and rheology. So really, it's just a wide breadth of physics phenomenon that you can model. So in terms of what STAR-CCM is capable of, the software accepts geometry, and then you run simulations on that geometry, and it's capable of accepting geometry from a wide range of CAD formats. So you can import. It's built off the Parasolid file. That's the one that it's really used for, or its geometry engine is built off of the Parasolid, but it'll accept many different types of geometry inputs. And then also, I think it'll also accept, actual CAD geometry, such as from NX, like a .prt file. It'll take like part files from a wide range of CAD software. So in addition to accepting geometry from external CAD packages, it's also got a fully integrated 3D CAD modeler built in. A lot of software are moving to that, where you can model your CAD, you can run a simulation in the same software. And STAR-CCM is the same way. I found that to be fairly powerful and a really good tool in the right applications. So STAR-CCM has also started to build out integration with actual CAD packages. For example, in NX, there's an add-on that you can add you can actually create a mesh and refine it. And I think you can actually run a simulation from NX. So they've started to kind of like streamline the process of, drawing geometry and then analyzing it. And and that's something that we could possibly do a webinar on if there's interest. So if there's anything that I mention here and people are interested, feel free to leave a comment and say, hey, I'd really like to see more about this, because for sure we can do more webinars on detailed topics, and we're going to plan on doing that. So, okay, moving along, there are various core measures and specialized measures, which I'll hit on probably in future webinars, but you can mesh with different types of cells, like a triangular tetrahedron or a polyhedron, or like a trimmed cell. And then there's different meshers which are specialized for meshing thin strips of material or directed tubes where you sweep along like a profile. So kind of similar to like a finite element mesh. It makes a lot of sense if you have like a finite element background. Another big thing I think that's kind of like a new wave in CFD is solution-aware mesh adaptation, where you don't really want to make a super refined mesh throughout the entire model because it'll blow up your runtimes. So instead, after a couple of iterations during the solution, STAR-CCM will reevaluate the mesh and say, okay, I don't really need it to be super fine here, but it looks like there's a shock here, so let me refine this region so I can more accurately capture that. That's a really big movement, and I think very powerful for applications where you have shocks moving around or combustion, that type of thing, where you have to like actually follow where your mesh density can follow the flame front and reduce the runtimes of your models really significantly. STAR-CCM can also tolerate moving and deforming meshes. You can specify like a rotating tire or propeller in a steady state simulation, and then you can also of course do steady state and transient simulations, so time dependent and not time dependent. There's also software capability for design explorations where you can set design variables and then have STAR-CCM just like run through the whole basically design space and tell you, hey, this is the best direction to go in. And then there's also automated and manual CAE integration, which means basically you can tie together, say, Femap and STAR, or Simcenter and STAR, and have them run in a loop. So you can basically have two-way fluid structure interaction. And then also, of course, you can have manual where you can export like a pressure field from STAR, and map that onto like a Simcenter model. So tons of capability with this software. Like digging into this software, I've really realized like how many things you can simulate, and you can really get into the details. So moving along, today we're really going to be talking about CFD because that's what we'll be using the software for. But at its core, CFD, it's a mathematical model that you solve using numerical approximation methods. STAR operates using a core set of fundamental laws, and those laws are set by the physics phenomena that you're simulating, and then that becomes your mathematical model that then you solve using an iterative method, which is numeric approximation. So for CFD, it's really the Navier-Stokes equations that you're solving: conservation of mass, momentum, and energy. And then, these are partial differential equations, and you have a larger number of unknown quantities than equations. So there's a couple of constitutive relations and models that you add in to help you provide closure to the mathematical model. So in addition, as part of the numeric approximation, the solution domain is discretized into a finite volume mesh, and these equations are solved for each cell or element, allowing you to have fairly accurate solutions with a sufficiently refined mesh. So this is one of the key differences between STAR, like a CFD solver, and a finite element solver. You kind of have to think about it backwards if you're used to one or the other. With a finite element solver, you mesh the structure, the solid. But with STAR and you're doing CFD, you mesh the volume of fluid around that solid, and that's definitely a key concept to wrap your head around if you're getting into CFD. Okay, so let's get into the user interface. This is what the STAR user interface looks like. You've got a toolbar on top, a simulation tree on the side, a properties window, an output window, and then the graphics window. The simulation tree is really where most of the action happens, and you watch the action that happens output into the graphics window. The simulation tree, it really follows the workflow of STAR-CCM. So you start with geometry, you import the geometry, and then under this tab it contains, or under this like folder or tree, it contains all the geometry preparation operations that you need to do, and then all the meshing. It's all done underneath the geometry node. And then for the continua contains your physics models, your part interfaces, starting conditions for your model. Basically, all your physics values are contained within the continua tree. So you can see how you would kind of follow this tree by importing your geometry, setting up your physics models. Regions is where you start specifying boundary conditions, a little bit more physics conditions. These are the three big tabs that you have to work through before you can actually run your model. And then you have stopping criteria, which there's tons of options for stopping criteria, but a common one is, after a certain amount of iterations, like 1,000 iterations, that's when I want the solution to stop. But as another example, you could set up a stopping criteria where you're looking at convergence of your model. Like after my model has met this convergence criteria that you set up, then I want my model to stop. So there's a lot of flexibility there. And then you have monitors and plots, which you can set up monitors to evaluate values of your model while it's running, and then plot those values over time through plots. Those are really, really powerful tools for visualizing data, extracting data from your model, that type of thing. And then scenes are huge because, that's what you're looking at. You want to look at your mesh, you want to look at the results, plotted on the surface of your vehicle. So we'll try to go through these in some of the demos. Okay, so the STAR-CCM workflow, it starts off with importing geometry. And this is something that I'll hit on a couple of times throughout this webinar. Your geometry in a finite element solver, it comes in as a surface or a solid. And in STAR, that's the same way. But in STAR, you're interested in the surface mesh of your geometry. And when you import your geometry, it comes with a surface mesh from the Parasolid engine that drives your geometry. And we'll get into that. But a key topic to understand is that when you import your part, it's already got a mesh. And a lot of the work in STAR is, operating on that initial probably coarse mesh to get it into something that you can then transfer into a volume mesh. So you have a lot of geometry preparation to do before you can even really start, what people typically think of as meshing. So yeah, those are the two things that we'll get to today, and we'll only briefly touch on them, but the rest of the workflow is, specifying your region and your boundaries, because if you're looking at a wind tunnel model, you need to ensure that, maybe you're working with a half model and you need a symmetry plane. That's one type of boundary. Or you need, like an inlet and an outlet, or a wall, where you don't really care about resolving the boundary layer. So you can turn off that type of functionality. And then after you've processed all your geometry into a good surface, you may want to continue processing the surface. So there's more meshing that you can do to get a good surface mesh. And then once you're finally happy with the surface mesh, you can then you move on to meshing the volume or the domain. And then of course, physics, boundary conditions, solver settings, setting up your reports and scenes, and then running. And then post-processing results, which is a whole nother, that's a whole nother webinar. So, okay. The first step in a simulation is, importing geometry. There's several options. There's several different ways you can do this. And the simplest way is to just import as parasolid. And as I said earlier, it imports a surface mesh. And I've got pictured here an example of an imported surface mesh. And you can see, like, it doesn't really look like a finite element mesh. It doesn't really look like a CFD mesh that you see regularly, and that's because it's just what's coming out of the parasolid. And you have to work on this mesh to process it into something that you'll get accurate CFD results. It's really just a triangulated surface. But if you have the software, the way you import is going File, Import, Surface Mesh, and see there's a ton of other options. So in addition, another option for importing geometry is to import it into the 3D CAD Editor. And this is actually going to import your parts as like a part file from NX, for example. It'll tolerate a bunch of different CAD packages, but NX is what I've used before. So if you import your CAD model, it preserves a lot of the CAD data that was originally defined in the model. And in the 3D CAD editor, you have a little bit more control. You can establish design variables, for example, control surface angles, or like a landing gear, so you can actually change whether it's out in the flow stream or not. There's tools for defeaturing your geometry. There are tools for extracting internal or external volume. So one example I'll give there is, let's say you have like an intake manifold for an engine. You have the intake manifold modeled, but you don't have a solid body for the volume of fluid that's flowing through it. So the 3D CAD editor has tools that will allow you to extract this volume without having to go into your CAD package and figure out, okay, what operations do I need to extract that volume? So some other advantages of the 3D CAD editor are that it allows you to set up some boundary names prior to converting your part into a quote geometry part, which has a surface mesh. And then it also allows you to pass an update to this CAD directly through the meshing workflow pipeline. So if you have something that you need to change, say you forgot, or you want to explore some sort of design variable, you can change it in the 3D CAD model. It'll auto update in the geometry part that has a surface mesh, and then all your mesh operations, you can rerun those and very quickly pass that update down to the point where you're just ready to click run. And it's very, very easy. It's not like you have to tear the whole model apart. So there's definitely some advantages to the 3D CAD editor. I will say that after you become a more advanced STAR-CCM user, there's probably times when it would actually be faster to just automate this with code instead of going into the GUI 3D CAD editor and doing it that way. But if you're doing like a once-off simulation, this is a really easy way to do it without getting into the code and the API. So like I said, the imported parasolid surface mesh is often, inadequate for generating a volume mesh. There's often too much detail, intersecting or gapped parts. Your part may have holes in it, and you need a watertight body in order to simulate it, because you can't have air passing into this into your aircraft or something like that. That's a big check that you have to watch out for. And then also non-manifold edges will cause a lot of errors and you can't mesh. So those are things that you need to solve in the geometry processing stage before you can even move on to anything else. So again, you have to process your geometry into a surface mesh that's then capable of producing a high quality volume mesh. Okay, so there are a few tools available for geometry preparation. The surface repair is fairly manual, and you have to go in and click on different edges and merge them, that type of thing. So if you have a lot of errors, that can be almost impossible to do if you have a really dirty geometry. So they have automatic surface repair, which will just clean up your geometry how STAR-CCM thinks you should. That works a lot of the time, but sometimes it changes things in ways you don't want to. So there's another tool called the surface wrapper, and it's actually a mesh operation, but it essentially works by shrinking a you can think of it as like a balloon. It shrinks onto your part, and you can basically defeature your part that way, or close gaps, cross gaps. Like if your two parts aren't exactly meeting, you can kind of fill in that void. That's a super powerful tool for A, defeaturing your part, or B, I guess you can kind of think of it as like merging all your bodies into one. So there's also plenty of geometry operations that I think you'd be used to if you're a CAD user. You can add surfaces together, split faces, that type of thing. And then once you've operated on different parts, you can unite, intersect, and extract their volume. So let's get into some of the software. All right, so here is the user interface. I've got a couple different files opened up here, but let's just cover the toolbar real quick. You can open a new file here or load a new file. There's a couple different options for saving, copying. You can record macros if you want to automate, GUI operations. You can import a surface mesh, which is a lot of what I do. It's the same thing as going to File, Import Surface Mesh, but it's just a button here. You can import you can launch a surface repair. That's another tool for correcting, invalid geometry. And then there's a couple options for initializing a solution and meshing, and then actually running your simulation. You can run one iteration, or you can run just to completion. And then all these operations here are for interacting with the graphics window. So I'll go ahead and open up my scenes here. And here's just a small test model that I've assembled. This is probably one of the most used buttons that I use. These are basically templates for scenes that you can set up. So if you click geometry, it's going to create a new geometry scene, and this is geometry scene 1. Yeah, so it'll create a new geometry scene with a couple, these are displayers. And it does kind of what it says it's doing. This one displays surfaces, and this displays outlines. And I don't really want this. So you can change the displayers within a geometry scene. That's why I said this is a template, because you can obviously create an empty scene and then add whatever displayer you want. So if I wanted to display surfaces, I can add a surface. And you can also add to the templates. So it's really customizable. So let's go back to this scene. I've got this geometry in here. It's a part that I've imported just as a surface mesh. And if I go into here, I can control which parts I'm showing. So clearly I'm showing pretty much the entire model. So there's options for, resetting your view if you want to center, if you get like really far off. Just a kind of a classic feature in any CAE software. You can rotate your model around. You can zoom in on certain regions. And then if you want to snap to a certain view, there's some really powerful options for doing that. You can change your perspective, but then you can change your view. So here, I'll give a quick demo. Let's say I want to look at this surface and I want Z up. So it's going to be the X normal direction plus X, and then I want Z up. And there we go. It just snaps to that. And you can cycle between these different views back and forth. You can save them. You can go to some pretty standard views. There's lots of options for snapping to different views, which is something that I do a lot in my FEA package. So when I learned about this, I was pretty happy because like in Femap, you can't click and just snap to a certain direction. Okay, some more options here. You can turn a surface transparent, and you can measure different dimensions on your part. So this is, 0.15 meters. So I found this to actually be pretty helpful, and it must figure out somehow which dimensions you're measuring in. But it's for the most part I found to be right. So you can show the mesh, and again, this is a surface mesh. So when you import your Parasolid, it's just automatically got a mesh associated with it, and it's just a triangulated mesh. Basically, your Parasolid mesh from your import is the simplest way to represent your part with a mesh. It's just got like two triangles on each face. Clearly, it's just like the smallest memory way to represent this geometry. And you can also turn off the mesh. So, and then there's a couple options for creating plots, which we'll probably get into in a later webinar, and then some selection filters. So, say I only want to select surfaces, or I want to select full volumes. So this is something that's available in NX and Femap. So if you're familiar with those, it's super helpful for like isolating certain faces or surfaces or curves. So, okay, I think that's it for this test model. Now I'm going to get into simple geometry operations. All right, let's go ahead and open up all my scenes. Okay, so this is the same model. Clearly there's a defect in this model. And I created this just to represent a super simple defect that you can easily fix. We'll probably do another webinar and really get into surface repair and how that works. But for now, I just want to demonstrate some of the functionality that's available. So if you go into your geometry tree and go to parts, we've got this body here. It's got surfaces, curves. You'll notice that it's got one face, but clearly there are 6 faces. So you have to split up the faces on your own, and STAR-CCM, it makes it pretty easy. There's a bunch of different options, but one that I like to use is split by angle, and it just you give it a certain angle, 89 degrees, and now I have 6 different faces, and I can select each one individually. Whereas previously it's just gonna select all of them. If you made a mistake, all you have to do is click here, right click, shift click, and combine. So there's another option, I think, if you split by part curves, yeah. So there's a lot of options here to explore. But for now, I'm just going to combine all of these. All right, so let's say I show the mesh. Clearly, there's a defect here. I want to get rid of this hole because when I'm running a CFD simulation over this part, I don't want flow to enter here. And if this hole still exists when I mesh the domain, it's actually going to mesh it's going to volume mesh the inside of this cube. So we want to close this so that it avoids doing that. You could close this hole with a surface wrapper. You could close this hole with an automated surface repair. I'm going to do the manual way and just click Repair Surface. If you right click, you bring up a ton of options. You can repair the CAD, you can repair the surface, you can edit the 3D CAD, but I'm just going to repair surface and accept the basic options. All right, so this is the surface repair window. You can actually check. I think I'll get into that in a second. So let's close up this hole. First, I'm going to turn on a selection filter for edges, and if you shift click, and then you can actually double click to select all the edges in around that perimeter. There's a bunch of different options here, but I'm just going to close. I'm going to fill the hole. All right, so now the hole's filled, but what if I wanted to get rid of these edges? I don't really want this feature edge here. Maybe it may mesh that edge and you'd still end up with some jank elements. So let's go back. Let's select these elements, or these faces actually. And delete them. We can actually go into the vertex selection. And collapse. And if you select all the right ones, it works. Clearly, I didn't select the right ones, but if you do it properly, it just zips all the hole into one vertex. One thing to note about STAR-CCM is that there's no undo button actually. So save early, save often, and save copies whenever possible. Because clearly I messed this operation up and I can't go back. So I just have to re-import my geometry, or that's it. So let's see. Oftentimes when you're editing geometry meshes, you'll be able to run these diagnostics. These tell you like what STAR-CCM is going to throw an error doing. So clearly we've got 3 pierced faces now that this operation didn't do what I asked it to do. We've got several free edges, and that's not going to work for this simulation. So this it's basically like a diagnostic toolbar and it allows you to quickly home in on problem geometry, problem faces, and you can actually like skip ahead one by one, and it'll tell you, like, it'll zoom in on it. So if you have a huge model with tons of errors and you think, okay, I think I can do this manually, if you click here, you can just step through and fix each one by one. Okay, let's move on to the next demo. Let's open up the scenes that I've prepared. All right, so this is more of a typical CFD simulation. You've got your domain, this big box, which basically represents a wind tunnel, or if it's large enough, just free field, free field stream of fluid moving around this vehicle. I've actually got it modeled as a half model, so you can see this aircraft here. I've got a symmetry plane, and then an inlet and an outlet defined. And you can put this together in several different ways. What I did is I've just got this part and I imported it directly from NX. So in NX, actually, I drew this box, this domain, and then I subtracted off my airplane model out of this box and ended up with this geometry. If you import just this aircraft into STAR-CCM, you can actually draw your own box and do the Boolean subtract operation within STAR-CCM. Okay, so let's look at the surface mesh from the Parasolid. Again, it's like the simplest way for the Parasolid engine to represent this geometry, and clearly, like, you got some really jank elements or cells that if you just straight up volume meshed the domain using this mesh, it would probably just not even work. So for that reason, I've chosen to remesh the surface. It's a mesh operation that you can do, and it doesn't actually change the geometry, but it attempts. It's basically like a retriangulation of the surface. You know, you're not worried about keeping this Parasolid file size down, so you can now increase the mesh density and get something that's more favorable. So if we go to the surface mesh, and I'll hide these faces for you, you can see here, this is a much more uniform, just a much better mesh that's going to generate a volume mesh of higher quality. And you can see there's a lot of refinement still missing. The leading edge is clearly not defined enough. There are definitely strategies for fixing this problem that I don't have time to get into today, but the surface remesher is a really powerful tool if your geometry is already fairly clean and you just need to retriangulate the surface. And I guess before I get too far into this, I'll show you where some of these operations exist in the model tree. So I've got my part, and then I've got a couple different operations. My surface remesher is what I've just talked about. It took my Parasolid mesh and turned it into this more clean looking, more uniform surface mesh. It's created by going operations new mesh, automated mesh. And oftentimes you'll do the surface remesher and you'll do the volume mesher in the same operation. So you can select both of them. And it'll skip producing this mesh and move straight to the volume mesh. But for now, in this one, I've only selected the surface remesher to show you all this intermediate stage, because when I was learning CFD, I really wish someone had explained this to me. It would have made all this make a whole lot more sense. Because this software is pretty complicated, and when you try to Google things online, you know, there's not a lot out there. So, yeah. All right. So let's say you're satisfied with this mesh. Obviously, you wouldn't be with this leading edge. If you think about it, if you actually have a leading edge like this in real life, that's going to cause a lot of problems. So in reality, I would put a local refinement along this leading edge, and I would definitely do a whole lot more refining before running this model. But let's say we're satisfied with this, and we wanna see what the volume mesh looks like. Again, at this point, we've only meshed all the surfaces, and we haven't created cells or elements within the domain that occupy volume. So I'll show you the volume mesh. I've used a polyhedral mesher, which creates cells with basically n number faces. I think there's a certain number, but clearly it's adopted the base surface mesh, and this kind of shows you why it's important to have a good surface mesh before moving on to the volume mesh. But overall, it doesn't look too bad, actually, aside from there's definitely some areas that I would refine. If we look at it from the outside, you can almost see a cross section of the mesh. It's coarse where, you know, there's not that many, basically where the gradients of different flow properties are small, and then it's fine where the gradients are high. And I've actually got a Prism layer mesh turned on, which helps you refine boundary layer characteristics. Obviously, this is super thick. I would need to make this much more thin. The boundary layer obviously isn't that thick, especially up at the front. But that kind of gives you a sense. There's just so many different options for refining your mesh and capturing different phenomenon. Yeah, so let's say you're starting fresh and you want to create a scene on your own. Let's go ahead and do that so it's pretty clear. Let's go ahead and create an empty scene, and it's named Scene 1. We can expand this drop-down. In the properties window, there's a bunch of different things, but normally I skip the scene properties and go straight to adding a displayer. Let's do a mesh displayer and then add a part to it. Let's add the entire airplane part. Click OK. And I'm left with a mesh scene. Okay. Clearly, there's something that we're missing. So let's see. I'll go back into mesh. Oh yeah, it's only showing the mesh. So let's show the surfaces as well. This is where it's important to split up your surfaces just for viewing purposes. When I imported this, it was all one surface, so I had to split the inlet from the outlet and the symmetry plane and the walls. So we can hide, we can hide here, and we can actually look in this domain and see the mesh here. If you're interested in like a slice of the mesh, there's options for doing that. Like if you want to look at a plane, you can definitely set that up, and that's something we can cover in future webinars. Okay, so let's say I want to look back at the original parasolid mesh. When you do these operations, it's operating on this part. So it may be hard to find that original geometry mesh, parasolid. So you can actually go back into the scene, into the mesh, and scroll down to representation and change which representation of your part you're currently displaying. So you can look at the volume mesh, you can look at the latest surface mesh, which is going to be this option. And this is what, again, our surface remesher produced. And then you can go all the way back to the geometry and look at this simplest representation of your parasolid. There's a lot of different options here, but one of the best ways to learn STAR is actually if you go to the help window and any of these, but I just go to help. And obviously this is contingent on you actually having the software. But you can go into the STAR-CCM help. It's probably one of the best documented softwares I've seen in a while. The user interface has just there's just so much documentation, help for everything, especially for modeling geometry. You expand one folder and it's just full of more information. So if you ever have a question, this is probably the first place to look. Obviously, we provide STAR-CCM support, so we're kind of the next line of defense. And then if we don't know the answer, we'll go straight to the makers of the software. So, all right, that's about it for this demo. And I think we're going to wrap this webinar up soon. But I want to show you one more feature that STAR-CCM has to offer. So in the geometry tree, you can see here, I actually have a 3D CAD model, and that's because I've imported a part file into 3D CAD, and then I've exported my bodies into parts, geometry parts. So the reason I've done this is, remember, this is one of the two options that I talked about earlier, where you can either import a surface mesh or you can import into 3D CAD and export after you've operated on your geometry, because there's a lot of functionality available in the 3D CAD modeler. So I've actually, let me go ahead and open this up in the 3D CAD editor. And let's show everything. I've got an aircraft here. It's obviously not really meant, this CAD model isn't really meant for a CFD project, right? There's holes, there are, these windows are different bodies, like all these are different things. It's not united. There's probably gaps, like between this cowling and the fuselage, or between the window. And this is an example of, you could probably fix this in like the surface repair, but it's almost easier to do a surface wrap and shrink a surface onto this to extract the outer surface. And you can also do that on the inside if you're worried about internal flow, where you like expand a balloon on the inside until it touches all the internal surfaces, and that way you don't have to do all this geometry processing where you have to unite everything. That's an operation that's not in the 3D CAD modeler though. That's after you've exported this into a geometry part, you can then create a surface wrapper operation. Anyway, so the one thing I wanted to demo here is that you can actually create a design variable that you can then automate analysis with. So for example, here I've got an elevator that's able to rotate around this axis, and I've just defined a design parameter which will change this angle based on what I tell it. So if I want to change this back to 5 degrees, and then update, it'll update that angle for me. And you can often set up STAR, as I mentioned earlier, to pass this update directly through the entire meshing pipeline. So you don't have to go set up all this stuff again. It'll just pass it through and you can run. Obviously, you'd probably want to check and make sure that it didn't mess up like some mesh transition, and you now have some like really weird cells that you need to fix. But that's something that's fairly powerful. And if you need to like I know for me, if I'm developing a load case, I'll need to change these angles around so I can get the correct attitude of the vehicle and pressure distributions. So that's something that'll be really helpful for me. All right. I think that's about it for today. Don't forget to leave comments if there's anything that you specifically want to see covered. I'll be doing another meshing I'll be doing a webinar on meshing in August, I believe. So keep an eye out for that. And if you have any questions, feel free to email us. I'll put my contact information up here. And I think that's about it for today. So thank you guys for coming, and we'll see you around soon.